Hello everybody, in this video I'm going to go over the different ways of writing functions, the notation, domain of a function, etc. Before we do that, I'm going to tell you why we're doing that, okay? So this is just calculus, and the way it works is, most of the time we're going to talk about derivatives, and then at the very end we will talk about integrals. Now, in order to define derivatives, we need to go over limits, and we're going to do that in the next video actually. And then in order to talk about limits, we have to review the concept of a function, okay? Perfect. So the definition of a function is it's a relation between two sets where every element in the first set is assigned to one and only one element in the second set. Okay, so what do I mean by that? By that I mean that if I have two sets, I'm going to call this set X, and this is my Y set, and say I have here 1, 2, and then here I have 1, 2, 1, 3. I cannot have one going to two elements in my second set, okay? That cannot happen. This is not a function, okay? This is the same if you think of it graphically. It has to satisfy the vertical line test, okay? So I have to have something like this, okay? i.e., it has to satisfy the vertical line test. It has to satisfy vertical line test. Hopefully you remember what the vertical line test says, but long story short, it tells you that if you can find, if you have the graph of a relationship, right? If you have something like that, and you can find at least one vertical line that touches the graph at 2 points or more, then this is not a function, okay? Perfect. Now, what's the notation? So say, for example, if I take conveniently, I'm going to call, I have here my X, which is the domain, and then Y is the range, okay? So I can say that my function, I'm going to call it F, I'm going to call my function F, it's a relationship that takes X to Y, okay? So the notation is that Y, it's actually equal to F of X, okay? And this we read F of X. Perfect. Actually, I'm gonna make this blue. I think there's a lot of green here, so I'm gonna turn it into color blue. Perfect. Okay. So now it's the same blue. Okay, perfect. So let's say, so now the first thing we did was we wanted to go over the definition of the notation of a function. Perfect, we did that. Now we want to evaluate a function graphically, okay? So now again, you know that this is a function because you don't have one value of X going to two values of Y, okay? That's it. So that's how we know it is indeed the graph of a function. Now, let's see. So if you want to find what F of -3 is, we know that this is, the x-axis is the independent variable, and then y is actually f of x. So if I want to know what f of -3 is, I'm looking for the y value. So this is -3. It takes me to this value right here, and then that tells me that y is equal to 6. So f of -3, it's equal to 6. Now, if we want to find f of -1, we'll do exactly the same thing. I find here the x value. So this is actually asking me to find the y value when x is equal to -1. So here I have -1, so the y value is just 0 because I'm on the x-axis. I do the same thing for 1 now. If I want to know what f of 1 is, I go here on the x-axis. I have to find x equals 1, okay? But then here, I happen to have two circles. How do I know which one is the actual y value? How do I know the value? Do I take 2? Do I take -2? And the answer is, in math and in graphs, whenever we have an open circle, that means that that value is not defined. Okay, one more time, that value is not defined. But then I do have a closed circle here, so that tells me that this is actually the value of the function. So here, when I find 1, it takes me to this closed circle, so the value will be 2. So f of 1 is equal to 2. Perfect. And then we have f of 6. We do exactly the same thing. Now that we review that, then we know that here, when I go to 6, I only have, it takes me here to this open circle. There's nothing else, okay? There's nothing else. So I'm going to say undefined. So one more time, whenever we have an open circle, that tells me that the value of the function is not defined there unless I have what we had here for 1, where even though we had an open circle there, it was closed at 2. Is that clear? I hope it is, okay? We need to understand this. Perfect. What else do we have? So now, so in math, we love undoing things that we just learned how to do. So in problem number 2, I gave you the graph of a function, and based on the graph, you have to tell me the values of the function, right? Evaluated at some x values. Now, I'm giving you the actual values, and I want you to give me the graph, okay? So it's the complete opposite. So let's see. So g of -6 is equal to 2. So I go to, so here I have -6, but it has to be equal to, when x is equal to -6, it has to be equal to 2. So I'm going to draw a little dot there. So let's have it right here, my little dot. That takes care of g of -6 equal to 2. Then g of -3 is equal to -4. I do exactly the same thing. I find negative here. I have -4. And it has to take me to, I'm lying, -3. Oh, here in between -2 and -4. It takes me here and then down to -4. So -3 and then down to -4. So that takes care of the second condition. Then it tells me that g of 1 is undefined. So if g of 1 is undefined, then I have to find 1. And it doesn't really matter where I draw this open circle, okay? If it's undefined, that tells me that I need an open circle. Open circle, and don't close it anywhere, okay? Just leave it open. So I'm going to put it, I don't know, who cares, right here. That's my open circle because it's undefined. And then I have one last condition. Now I know that g of 4 is equal to 0. So I know that y is equal to 0 when I'm on the x-axis. So here we go. Boom. That's it. And if I want a graph satisfying those 4 conditions, what I do is I connect the dots, okay? So I just connect the dots. And who cares? You can do whatever you want, okay? Boom, boom, boom. It's one function satisfying all 4 conditions, okay? So you could have done anything. I mean, who cares? As long as you have a function, so this is my g of x, as long as you have a function that satisfies that g of -6 is equal to 2, g of -3 is equal to -4, g of 1 is undefined, and g of 4 is equal to 0, okay? We love graphs, okay? We love graphs, so we will ask you to sketch graphs of functions satisfying conditions, okay? On every single test. So make sure that this makes sense. Perfect. So now I went over how we can define a function graphically, okay? Now we're going to go over how we define functions algebraically and how to evaluate the function if I define it algebraically, okay? So now I have that my function f of x is equal to x squared minus x. So if I want to find f of -2, I literally go back to the function and I plug -2 into the function. I replace every single x value with -2. Just replace it. So I get -2 squared minus -2. One more time. I literally replace every x value with the number in between the parentheses. In this case, we have -2, okay? So what this rule is telling me is take that value, square it, and then subtract it. That's what we're doing. We're taking -2, we square it, then we subtract it. So if I do that, I get 4 minus minus turns into positive. So 4 plus 2, we get 6. Okay, now we do the same thing for 0. So the rule tells me square x and then subtract it. So square x and then subtract it, you still get 0. F of 3, again, square x and then subtract it. So square x and then subtract it, you get 9 minus 3, you also get 6. Okay? And now hopefully you've seen something like this in college algebra, pre-calculus, your previous life, somewhere, I don't know. But we're going to use this. I'm gonna tell you why. This is gonna be part of the definition of the derivative, okay? So again, when I started talking about calculus, I told you that we would define the derivative. And now I'm telling you that you're gonna need this f of x plus h in order to do so. So let's see how we do this. So f of x plus h tells me that I have to square what I have in between the parentheses and then subtract it. So square it, the whole thing. You take the whole thing and you square it and then you subtract it. Okay? So we have the function was x squared minus x. That tells me take the variable, take the independent variable, take that value, square it, and then subtract it. And that's what I'm doing here. I'm squaring and subtracting, okay? So then, of course, you all know this. X plus h squared is equal to x plus h times x plus h. I know you know this, but I'm just going to write it. I'm going to write it and then I'll erase it. Okay, so I know that if I have x plus h squared, that is actually equal to x plus h times x plus h. And I have to FOIL this thing, okay? So this is equal to, first, so x times x, you get x squared, and then x times h plus h times x, you get 2 of those, so 2xh plus h times h, you get h squared. You got that? Perfect. If you didn't, then go review how to multiply two binomials, okay? So long story short, now I get that x plus h squared is x squared plus 2xh plus h squared. And then I'm subtracting x plus h, so I have to distribute that negative, okay? And I get minus x minus h, okay? So one more time, and I know you got this. I know you got this, but let me just review. So this x squared plus 2xh plus h squared, this is f of x plus h, okay? And then minus x minus h, this whole thing represents minus f of, I'm lying, it represents minus x plus h, okay? Perfect. Now, the domain of a function is the DNA of the function. It tells you the values that are legal, the values that you can actually plug into the function, okay? So let me define domain. So the domain of a function is largest subset of the real numbers that you can plug into the function and get a real and defined value. That's it. So we start with all the real numbers. We start with the real numbers. I'm going to take the largest subset that you can plug into a function and get something real and defined. What do I mean by that? So by real, I mean that I cannot have negative numbers inside square roots or even roots, right? So by real, let me take a different color. Let me take green. So by real, I mean no negative inside square roots. Huh, how convenient. And define means no division by 0, right? We know that whenever we try to divide by 0, we say, oh, it's not defined. Oh, I cannot divide by 0. Oh, it's not defined. So I cannot divide by 0. You cannot divide by 0. Nobody can divide by 0. Okay? So let's do it. So we have to discuss domain of these functions. And I start with x over x plus 1. I start with x over x plus 1. So long story short, I start with all the real numbers. And I look at my function and I go, do I have a denominator? Do I have a denominator? If I do, then I have to get rid of the numbers that would make that denominator 0, because division by 0 is not defined. Okay? So I know, if I do this first example, I know that x plus 1 is equal to 0 whenever x is equal to negative 1, right? So I'm going to say if and only if x is equal to negative 1. So then that tells me that I can substitute any real number, right? I can substitute any real number. I can substitute 0, root of 2, 5, pi, negative 200, whatever you want to substitute, except for negative 1. Because if you do, then you would get negative 1 over 0, and that is not defined, okay? So how do I write that? I say, well, the domain is all real numbers, so real numbers, except negative 1. One more time, we don't want negative 1 because it makes the denominator equal to 0, okay? Therefore not defined. Perfect. Now for the next example, I have root of x. So no denominator means that I don't have to worry about dividing by 0 because I'm not dividing. But I do have a square root, okay? And the first part tells me that I have to have something real, meaning no negative inside the square root. I cannot have negative numbers inside the square root, okay? That tells me that I need whatever is inside the square root to be greater than or equal to 0. So I need x to be greater than or equal to 0. And that's the domain of my function, okay? That's the domain of the function. So what's my domain? All real numbers larger than or equal to 0, period, okay? Now, imagine for a second that instead of having root of x, I had root of x plus 1, right? So I would need x plus 1 to be greater than or equal to 0. So now the domain would be x greater than or equal to negative 1, okay? So it's not that you need x to be greater than or equal to 0 at all times. You need whatever is inside the square root to be positive. Well, non-negative, 0 or positive, okay? Now, do you see what I did here? Do you see what I'm doing here? Right? Do you see what I'm doing here? Not only do I have a square root, I also have a denominator. So it's like I'm combining the first two examples, okay? Now the domain would be very similar to the one here for root of x, because I have root of x here, but I have to get rid of 0 because I'm not allowed to divide by 0, okay? So think about it for a second. Not only do I need x to be greater than or equal to 0 so that the square root is defined, I'm dividing by it, so I cannot have 0 denominator, okay? So now my domain will be all real numbers greater than 0. One more time. The domain of root of x is greater than or equal to 0, right? It could be equal to 0, but if I'm dividing by it, I have to remove that. I hope that's clear. Because in this class, everything boils down to computing the domain of a function. Everything. Okay. Fourth example. Now I have my favorite polynomial, by the way. We have u squared plus 3u plus 5. The domain of this function, think about it for a second. No denominator, no problem. No square roots, no problem. Nothing weird happening. This is actually a very beautiful, cute polynomial. Domain, all real numbers. And think about it for a second, right? I'm going to write it like this. Real numbers are all real numbers. You can substitute whatever you want. You can plug in whatever you want, and you will get something real and defined. No problem, right? Something real and defined. Okay. Next function, we have cosine of theta, okay? Cosine of theta. Again, you can substitute whatever you want and you'll get a value back, okay? So all real numbers as well. And now we get to the, the last example. Now we have x squared minus 4 over x plus 2. If there's a denominator, you're not allowed to divide by 0. Therefore, we know that this fraction will have a denominator equal to 0 whenever x is equal to -2. So my domain will be all real numbers except for -2. So I'm going to say x cannot be equal to -2. Because if it is, then the denominator is equal to 0 and you're dividing by 0 and that is not allowed. It's undefined. Perfect. And now we have one more example. Okay, now hopefully when you were thinking about the domain of x squared minus 4 over x plus 2, you thought, wait a second, I can factor that top, cancel the denominator, and then I'll be good to go, right? It's like nothing happened, okay? And that's why we care about looking at the difference between the value of a function at a particular x value and what happens as x gets closer to that value. Let me tell you what I mean by that, okay? Let me tell you what I mean by that. Hopefully in college algebra, maybe second grade, maybe somewhere you learned that here, when you have x squared minus 4 over x plus 2, that actually, so we have x squared minus 4 divided by x plus 2. Hopefully you've seen that this is just equal to x plus 2 times x minus 2 all over x plus 2. You're able to cancel x plus 2 and x plus 2 and you get x minus 2. Okay? And hopefully, you remember that the graph of x squared minus 4 over x plus 2 is just the graph of x minus 2 with a hole at x equals -2, because that number is not in the domain of the function, okay? Hopefully you remember that. So let's see what happens. Let's see what happens with this function, okay? And this is just a little experiment, and the reason why we're doing this will become clear next time, okay? In the meantime, I know that -2 is not in the domain of the function. We did that already, okay? It's undefined. It's undefined. But then, what happens when you do f of -2.01, f of -2.001, f of -2.0001? What do we get? What do we get? Well, f of -2.01, I have to do it. I don't have my calculator. Okay. Are you doing it? Okay, so if I substitute -2.01, I get that this is -4.01. If I substitute -2.001, I get -4.001. If I substitute -2.0001, I get -4.0001, okay? Yes? Now, if I substitute -1.9, actually, let me start from the right. So if I substitute -1.9, I get -3.9. If I substitute -1.99, I get -3.99. If I substitute -1.999, I get -3.999. If I substitute -1.9999999999999, I'm going to get -3.999999999. So we know that -2 is not in the domain of the function. Why? Because when I plug it in, I divide by 0. I get 0 over 0, right? But do you consider that the value of the function gets closer to a number as the value of x gets closer to -2? Right? Do you think that the value of the function is getting closer to a y value, right? To a value of a function? Yes or no? Yes or no? The answer is yes. And by getting closer, I mean I can be getting closer by taking numbers. I can be getting closer to -2 by taking numbers greater than -2, or I can be getting closer to -2 by taking numbers smaller than -2, right? It doesn't really matter how I do it. The truth is that this seems to be getting super, 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 super close to -4, right? Whether I take numbers smaller than -2 or larger than -2, the y value is getting closer to -4, okay? So I'm going to say yes, actually, yes. It is, I'm going to say the y value or the function. So the y value gets closer, and I'm going to say closer, what does it mean to be closer? It gets closer to -4 as the x value gets closer to x, okay? And what's going to happen is that this is actually the definition of the limit of a function, that concept that we need in order to define the derivative of a function, which is the whole point of calculus, okay? And that's all I have for this video. I'll see you next time.